Good morning, everybody. I am Eddie, and I'm another TA for this functional programming course. Today, we're going to look at an exercise about higher order functions, namely an exercise about church numerals. When we think about the representation of a number, we can see that we can represent a number in many different ways. We can represent it using decimal numbers, like 1, 2, 3. We can represent it using binary notation, so only using zeros and ones. But we can also represent it in any other ways. For example, with a string of stars, in which each star represents a unit. Now, when we talk about church numerals, we talk about a way to abstract over this concrete representation of a number by means of functions and function definition. Okay, now let's see how a church numeral works. The type of the church numerals is this that you can see here on the slide, and it's basically a function that takes as an input argument another function, namely, we will see that this function is called the successor function. It takes another element, another argument, which is the zero number, and it returns the church representation of this number. Ideally, a number n is defined as n applications of the successor function over the zero number. So now let's try to actually write these type of numbers so that we see more or less how they look like. So we said they are represented as a function that takes as an input parameter an s and a z. And for example, the zero representation returns only the zero number. For the representation of 1, we apply the successor function only one time. For the representation of 2, we apply it twice. Now we can see that since we're Haskell programmers, we don't like a lot of noise in our code and all. We can refactor our representation of 2 by using the composition operator. So then we can write s.s, and then using a technique that comes from lambda calculi, namely called eta reduction, we can remove the z argument and just show this implementation of 2, which is exactly the same from the first one. Now, these are the representation of the church numerals, but as you can see from the type, the A tells us that they are polymorphic. What does this mean? This means that we can instantiate them to represent a number in any concrete representation, and this is what we were saying from the beginning. Therefore, this A can become an integer, can become a string, can become anything else. Let's try now to write some functions that actually instantiate these church numerals to concrete representations. And for example, let's write a function church2int. This function will take as an input argument a church representation of a number, therefore a function, and we'll apply to this a successor function that will be only the +1, and a zero number that will be 0. We can see here an example. So the first argument is the only argument is 2, and then we apply to this +1 and 0, and this is how this. Once we substitute, we see that we apply +1 to 0 the first time. Once we have done this, we will apply +1 to the result of that, which will be 1, and which will give us 2 in the end. Now, as I said, we can instantiate this function not only to integers, but to other things as well. And for example, we can do it for our example with strings from before. Now, the successor function will append to the string, at the head of the string, the star, and the zero operator will be the empty string. Here you can see an example in the slide. And again, we apply this to the number 2, and we see that first we cons a star to the empty string, and then we cons again to the result of that, which will be the string containing only the star, only one star. We will cons again another star, and we will have the representation of 2. Now, here we have, up until now, we have described what a church numeral is, and we have described how to instantiate it to a concrete representation. But what we have to do now is we need to define operations over these numbers so that we can actually manipulate them. To do this, we will try now to derive an implementation of addition. So we start by taking two definitions. So we have x prime and y prime, which are church to int of x and y. So x and y are church numerals, and their church to int version is an integer. And what we want to achieve in our derivation is that the integer addition of the integer representation of x and y equals church to int of a function that we will define later, add, of x and y defined over church numerals. Okay, to do this, let's start easily. So we say, okay, x prime plus y prime just equals the representation from here, church to int of x and church to int of y, plus church to int of y. Now we expand the first definition, church to int of x, with our implementation of church to int. So we'll apply to x the successor function plus 1 and the zero number 0. Now what we can see is that here we are building up 0 starting from the 0 number which we gave ourselves, which is 0. But then we say, okay, but after this we want to add another integer, which is the integer representation of y. So why don't we just start building x instead of from 0 from the integer representation of y itself? Okay, we can see that by generalizing a little the church to int function, this is really easy. So if the church to int function would take another parameter z, we can substitute the 0 to a parameter defined by the user. And so we can get this church to int and move it inside as the base number of the representation of x. What we do now is we expand church to int of y, again with the same definition of church to int. And what we can note now is that we have two instances of plus 1, of the plus 1 function, and then one time we can find the zero number. So, but why don't we get those? We abstract them out with another trick from lambda calculi, which is called beta expansion, and we create a function out of that. This is this step. Here I have highlighted plus 1 and successor and all the names so that it's easier to understand. What we have basically done here is we have extrapolated, expanded that, that term that we have, that expression, into a function that is then applied to plus 1 and 0. So these two terms in the last two lines are exactly the same. What we do now is we can get this, this lambda, and we can give it a name just because it's easier for us to see. So let's call it add. Now I will explain you in 1 second why add, but let's call it add, and we see that we need to parameterize it over x and y because they were the only two free variables in the definition above. And if we take a look at this function, we see that it's just an application of the church to int body of the function that we defined before. So we can just substitute that, and we see that in the end we have arrived to our definition. And this was really easy. We didn't really do anything. We just mechanically substituted and used a few tricks from lambda calculi to arrive to our answer. So finally, the definition of addition between two church integers, church numerals, is a function which will be actually a church numeral, which will build x with the successor function, but starting from the final representation of y, and therefore giving us the addition of x and y. Now, we have done the addition. Let's try now to define the multiplication. When we think about multiplying two numbers, two decimal numbers, what we know from school is that what we do is, let's say we want to do 2 times 3, then we want to add together 3 times the number 2, and this is what this here thing says. Now, when we want to do this with functions, we cannot just add functions together, but we can compose them. So the idea is basically the same. We want to, every time, for 3 times, we want to concatenate, compose the definition of 2. And we can see it here, that 6 will be the composition. If we substitute S with the composition, with the definition of 2, we can see that 6 will be just a composition 6 times of the successor function. Now, therefore, the multiplication will be defined as a Church numeral again, which will take a successor function and a 0 number. And we'll apply a different successor function to S, which we can call it a super successor, which will contain y exemplars of the successor function. And therefore, we will have the multiplication. We can, furthermore, clear up this definition with, again, a few tricks from lambda calculi, and we can just express it in this way nicely with composition of x and y. So that was it for Church numerals. In the exercises, you will see a few more tricks that we can do, for example, exponentiation. And then there will be on the course page another link to furthermore get more information about this representation. Thank you for listening, and happy hacking.